Alcohols can act both as acids and as bases. This puts them in a category of compound we call amphoteric. Let me first talk a little bit about these compounds as acids, and then I'll talk a little bit about these compounds as bases. I've listed a few simple alcohols here, along with water, and shown their pKa values. You see methanol is at the top, it's more acidic, and tertiary butyl alcohol is at the bottom, it's less acidic. But you see the differences aren't great, especially ethyl alcohol and methyl alcohol compared to water. So our bottom line, if alcohols and water have similar acidities, then when an alcohol is put together with a base like sodium hydroxide, an equilibrium is established. And because these guys have similar acidities, alcohol and water, this is going to be a true equilibrium with significant amount of both alcohol and water on each side of the equilibrium, which means using sodium hydroxide is a very poor way to make alkoxides. We're going to have to look for a base that's much stronger than NaOH, so we can shift the equilibrium all the way to the right if we want to prepare sodium alkoxides. Well, here's a couple examples. You can make alkoxides by using a very strong base which shifts the equilibrium far to the right to prepare the alkoxide in essentially quantitative yields. In addition, in this case, hydrogen gases evolve, and as hydrogen gas leaves, it also shifts the equilibrium. So using sodium hydride is a great way to make sodium alkoxides. A second way that's very common is to use sodium metal. Again, hydrogen gases evolve, and again, this reaction is essentially quantitative. So using either sodium hydride or sodium metal, we can transform alcohols into sodium alkoxides. Why would we want to do that? Well, because sodium alkoxides are both good bases and good nucleophiles, so we can do a lot of chemistry with those guys. Alcohols also act as bases, but they are weak bases. Actually, they're very similar to water in basicity, just like they're similar to water in acidity. So, weak acids don't protonate alcohols to any significant extent. It takes a strong acid. We can follow that proton transfer using our arrow pushing. Recognize that there's a lone pair of electrons on oxygen available for sharing with that proton as that pair of electrons stays with the other portion of the acid. As a result, we make a protonated alcohol, which is positively charged, and then also the counterion, the anion, which is negatively charged. Again, this only happens if we're using very strong acids. Typical examples include sulfuric acid, hydrochloric acid, hydrobromic acid, and we'll see reactions of alcohols using all three of these strong acids. In every case, these acids protonate alcohols to a rather large extent, and the significance for their chemical reactivity is the transformation of a very poor leaving group, the hydroxyl group, which means substitution doesn't happen with alcohols, into a very good leaving group, the protonated OH, which will leave as water. So for the protonated alcohols, substitution happens. And for this reason, sulfuric acid, hydrochloric acid, and HBr all are good catalysts for substitution reactions. And as we'll see also, using sulfuric acid, this protonated alcohol has a strong tendency for elimination to make alkenes. So, in summary, alcohols are weak bases. Strong acids protonate them sufficiently to transform a very poor leaving group, OH, into a very good leaving group, water. And that's how strong acids catalyze reactions of this very weak base,